I'm Carl C. Eulis from Nowhere, North Carolina. I've been smithing for 15 of my 27 years, and I'm here to show my proof.
Howdy, name's Leonard. My friends call me Oily because of my work. I'm a professional bladesmith from Jacksonville, Florida, here to prove myself to my dad, Billy Bob.
Hello, my name is Algebra, but people call me Al. I'm from Anchorage, Alaska, and I'm here to prove my professors wrong.
Welcome to the Forge. It's good to have you guys. You're all here to test your skills, not only against each other, but against a series of grueling challenges. At the end of each challenge, you will present your blade to our panel of expert judges for inspection. Those judges are
Historic Weapons Recreation Specialist David Baker,
and me, Edged Weapons Specialist and Kali martial artist Doug Markita.
For your first challenge, using the resources available to you in this forge, you will create a small bladed-like weapon, like this. There are a few parameters. Your blade must be 4 to 6 inches and must include a full tang handle construction.
I've been really impressed with the other contestants. I've never seen someone straighten a parabola bar with a derivative.
This blade is a great side profile. However, there are some glaring issues right off the bat. For starters, the handle's a little bit too wide and it actually hurts to hold.
Most importantly, however, there's a noticeable crack on the handle of the blade. There is a notable issue with the cusp on your handle, making it non-differentiable as well as unsafe to test. Because of this, we will please ask you to leave the forge.
I understand. While things may not have worked out for me in the forge today, I'm glad I had this opportunity to test my skills. And maybe now I'll make sure to warm up my calculus skills before handling any more blades.
Now, for the moment we have all been waiting for, the only thing between one of you and a Factored and Fire champion, as well as a check for $10,000, is one more challenge.
But this challenge is no joke. It involves one of my favorite tools from history, the hatchet. This simple tool has existed in various forms since the dawn of humanity. We would like for you to go back to your home forges and make us your own signature axis.
And when you get back here, your weapons will be subjected to 3 dynamic tests. On top of this, Smiths, you will only have 3 days to complete these axes to the parameters specified in these booklets. Best of luck.
Ooh, that was a close one. I almost hurt myself there for a bit. Fortunately, I get to go back to my home shop with tools I'm familiar with and methods I'm used to.
Gotta say, really fun during the elimination round. Very out of my element to work in such a tight time frame and in a unique environment. Way more thrilled to go back to my home forge and really, be able to put the work in.
Alright, here's a quick update on the handle. I decided I wanted to be about 3/4 of an inch at the narrowest and about 1 inch at the broadest. I wanted it to be a nice hyperbolic shape to really get a good grip in there. And I wanted it to be 4 inches long, so I got the equation x squared minus 7 over 256 y squared equals 9 over 64. And I really want a nice smooth transition into a circle down here to make sure that no one's hand slides off and it's not sharp anywhere. So I drew it up in CAD and I got this, and I have a circle I need, but I need the center point and I need the radius. I know it's going to be in line with x equals 0 because it's going to be in the center because when I revolve this profile. So that gives me the circle equation, x squared plus y plus b all squared equals r squared, which is going to be my final circle. But I need this to be both continuous and differentiable, meaning both the position and derivative need to be the same at my point, 1/2 -2, which is where they will meet because -2 is the cutoff for the bottom of the handle. So in order to do this, I'm going to implicitly differentiate both of them to find their slopes at that point. So the derivative of my first one is 2x minus 7 over 128y. Don't forget the chain rule with dy dx, and then that 9 over 64 goes to 0 because it is a constant. Then now I simply just solve for dy dx, and I get x over y times 256 over 7. And then I'm going to do the same thing for my circle equation. Derivative of x squared is 2x plus 2, using the power rule, 2y plus b, chain rule dy dx equals 0 because this r squared is a constant, which goes to 0 because it's a circle with constant radius. Do the same thing again, solve for dy dx algebraically. So I subtract over, divide over, and I get dy dx equals negative x over y plus b. Now I actually need to figure out what the slope is at the point that I'm trying to match. So dy dx evaluated at 1/2 comma negative 2 is 1/2 over negative 2 times 256 over 7, using my derivative of my function from the last page. I just then simplify this down, eventually getting negative 64 over 7. So now I've input this into my derivative of my circle equation. So negative 64 over 7 equals negative x over y plus b. Substitute in my x and y values for my point that I'm trying to match, and I get 64 over 7 equals 1/2 over negative 2 plus b. Solve this algebraically, cross multiply, and then add over my 2, and I eventually get b equals 263 over 128, and b minus 2 equals 7 over 128, which is going to be helpful when we find our r value. Speaking of which, to find my r value, it's simple. I have it in terms of the 3 variables I already know, so I input b into my formula, and then I input my point into the formula, and I get r squared equals 1/4 plus 7 over 128 squared. Now, since I'm going to input this into my CAD program, it likes decimals to the thousandths place more than it likes fractions like this. So I'm going to use my graphing calculator, and I get r squared equals 253 thousandths. But since it's geometric, I need an actual radius rather than my r squared value. So I take the square root of that, getting 503 thousandths. Now my final equation for my tangent circle is x squared plus y plus 263 over 128 all squared equals 253 thousandths. I can now go back over here, and I can input my dimensions. So this one will be my 263 over 128. And this, since it's a diameter circle tool, I need to multiply it by 2, but that's not a problem. Times 503 thousandths. And then there we go. We have our sketch. Take this out into project, into model view, and just give it a quick revolve. Give it a quick revolve. This is not the most user-friendly software I've ever met. But there we have it. Nice and refined handle shape.
Alright, I saw how that round went for Al. I'm determined to learn from his mistakes. I need to optimize my time and resources to get the best results out of this competition. To do this, I'm going to find the maximum volume I can cut off in 180 seconds I have to get to work. To do this, I'm going to find the derivative of the volume, the change in the volume, at a rate of dv dx. When that equals 0, I can find the critical points where there will be a maximum volume I can calculate. With that, I can figure out the width and the depth, x, and then the height, y, to cut off. In order to start, I need to write down what I know. So I have 180 seconds, and then it takes 10 seconds to cut the width, as well as 10 seconds to cut the depth, and those numbers have to be the same as each other, and then 12 seconds to cut the height. To do this, I can do some algebra to combine some values, and then I can establish the volume is going to be the width times the depth, which is the same value, times the height. I want to isolate to have everything be in terms of x for the volume equation to make it easier to solve. To do this, bringing out solving for y in order to substitute in. Once I can plug that into v, then I can take the derivative of it to, and then I can optimize. Just continuing here, distributing the x, make it a more simple. Small writing errors always happen when you're going fast, but ends up working. Should be and then with that we can set the rate of change of the volume equal to 0 and then solve for x. This is some real basic factoring to take out an x and then take out that 5. And then at this point we can see that to equal 0, x can either be 0 or x can be equal to 6. And these are the critical points that I'll need to check for if they're a max or a min. Additionally, I'll need to check the endpoints because there's always a chance that those could be a maximum. In this problem, the height cannot be less than 0, can't have a negative height. And the x also cannot be a negative value. Smallest you can cut something is none. And then in order to solve this, we can figure out what x is when y is at its most extreme value. Because we already know that x equals 0 is a critical point. So if we plug in 0 for y, we can solve. That shows that the largest x value possible is 9 inches. And then we can put that in as a point to test. Then if we take the second derivative, we can use that to prove concavity, and if that point is a potential max or min. I've just summarized by putting max or min. So that's the second derivative of volume, and then at second derivative of x equals 0, it is a positive number, which is 30, which therefore means it is concave up and is a local or a potential local minimum. At x equals 6 is equal to negative 30 and is therefore concave down and is a possible local maximum, but not necessarily the absolute. Actually, for 6, it's definitely a local maximum, but it's not necessarily the absolute maximum on this interval. Then second derivative of 9, which is the endpoint you have to test, is also a negative value, which means we'll have to end up testing again because it is concave down in a potential max. So then you can just plug this in, the volume at x equals 6, and this is using a summarized thing. Volume at x equals 6 is 180 inches cubed. I believe I miswrote that and only wrote squared. And then at x equals 9, the volume is only 0 because there's no height, so therefore it cancels out. So the max volume is 180 inches cubed. Once again, miswrote that. And then the dimensions are 6 and y. I'll throw up on the screen and post the math to do that, but we're using the 180 seconds equation. Therefore, the height should be I should cut is 5 inches and the width and depth is 6.
Welcome back, Smiths. I hope your fortune went well. We asked for 2 unique blades, and you certainly delivered. Carl, you clearly adapted the design quite heavily. Great use of material. I commend your efficiency.
Thank you. They don't call me an optimist for nothing.
Leonard, you certainly produced a polished piece, and that handle is certainly well thought out.
Why, thank you. I think it turned out well, although I think I got chronic pain now.
Alright, Smiths, as you know, your axes will be subject to 3 dynamic tests. First up is David Baker with his patented differentiability test. Take it away, David.
Carl, your handle has a small issue, that it is only approximated with a second-degree Taylor polynomial and is less accurate. But other than that, great job. Leonard, your handle is not only continuous, but also differentiable through the entirety of the grip. I really love this chain of concavity right below my hand. It really helps the grip. Now that I know I can hold your axes, it is time for my favorite test, their durability test. I will test each of your axes with a controlled amount of strikes on this natural log in order to see how much they chip. For Roman to give a good chance for the contestant's blade, he must hit the object at the right velocity, given that he will have a swing time of 0.8 seconds with his arm and blade being 3 feet long. Given the position vector of 3 sine 5 pi over 8 of t for the x position and 3 cosine of 5 pi over 8 of t for the y position, we will derive these positions for each component of x and y, and we will then use the velocity magnitude equation of dx dt squared plus dy dt squared using 0.8 seconds as t to find the speed at which Roman hits the object to be 11.314 feet per second. Carl, are you ready?
Ready as I'll ever be.
Spectacular, you passed with minimal damage.
All right. Thank you very much.
Leonard, are you ready?
Let's do this.
All
Yeah.
right, let's do this. All right, you're not making my job easy here. This axe also passed with minimal damage.
Thank you kindly.
Alright, now it's time for the dynamic cutting test. With this, I will be able to fully see the wieldability of each of your axes as I use them to slice some of Timmy's 10 factorial clementines from those Math 1 problems. Carl, are you ready?
Absolutely.
Alright, let's do this. Your axe will cut. Leonard, are you ready?
Conditionally.
All right. The blade of your axe was a little bit blunt, and as a result, the cut didn't pass through cleanly. However, it still did cut, and as a result, you passed the cut test. And the winner of the 2025 Factored and Fire Championship and the recipient of a $10,000 check is none other than Carl C. Eulis.
Woo! Go Eulis.
Well, congratulations to Carl. I felt like I did well. He just did a little bit better. It was such an honor to be here, and I would definitely do it again.
Incredibly proud of what I was able to do here. Very good job to Leonard and Al. I can't wait to see what the rest of us do next.